Welcome back to Chemistry 30. This is the EQ3.6 section, strong acids and bases. So in 3.5 we looked at pH, looking at potency of hydrogen, pOH, etc., and looking at how that relates to concentration of H pluses and concentration of OH minuses. Now we'll look at strong acids and bases and what that means. So we'll look at calculating the pH of a strong acid or a strong base given its concentration. The chemistry of an aqueous solution depends critically on the pH. It is therefore important to examine how pH relates to acid and base concentrations. So that's what we're looking at here. The simplest cases are those involving strong acids and strong bases. And in the next section we look at weak acids and weak bases. Strong acids and bases are strong electrolytes existing in aqueous solution entirely as ions. Let's highlight that. So what that means is that strong acids and bases completely dissociate or break down into H plus ions, or in some bases, OH minus ions. There are relatively few strong acids and bases. So if we look at some of the strong acids and bases, strong acids, hydrochloric, hydrobromic, hydroiodic, chloric, perchloric, nitric, and sulfuric. Those 7 are considered strong acids. Strong bases, any of the group 1A metals combined with a hydroxide are considered to be strong. And also group 2A metals combined with hydroxides are considered to be strong as well. So hydroxides are strong bases. Strong acids, so look at those first, then we'll look at strong bases and see that they're very similar in terms of how they operate. The 7 most common strong acids include 6 monoprotic, which means 1 ionizable hydrogen, 1 ionizable H plus. So here, HCl, so you can see there's only 1 H in each of those, whereas over here, di, mono di is 2. We have 2 hydrogens with sulfuric acid. Nitric acid exemplifies this behavior of the monoprotic strong acid. For practical purpose, an aqueous solution of HNO3 exists entirely as H3O and NO3 minus ions. So if we look at nitric acid in water, we could think of as the H being transferred to the water, of course, to make a hydronium ion and left with NO3. We assume that that completely happens. So all 100% of that H breaks off from nitric acid and combines with water to make hydronium. And notice we didn't use an equilibrium arrow because it is one-sided. It goes completely to the right. So it lies entirely to the right. That is the definition of strong, completely ionizing. Recall that we use hydronium and H plus interchangeably to represent the hydrated proton in water. Thus we can simplify it just to be nitric acid dissociates or breaks down into H plus and NO3 minus. And that happens 100%. So there's no reason to draw a backwards arrow because it all lies to the right. In an aqueous solution of a strong acid, the acid is normally the only significant source of H plus ions. As a result, calculating the pH is very easy because H plus equals the original concentration of the acid. Now that is true if it's a monoprotic acid, so we have that happening. So on the next page here, if we look at an example here, figure out the pH of a 0.04 molar concentration of HClO4, and it's considered a strong acid. And for the most part, I'll let you know if it's a strong acid. So HClO4, if it's a strong acid, what that means is that all of it breaks down into H plus and ClO4. So what that tells us, if our original solution is 0.04 molar here that we're told, 0.04 molar of that, when we have that acid in water, it breaks down entirely. Now notice this is a 1-to-1-to-1 reaction, so that makes it pretty easy. Down below we'll look at one that isn't 1-to-1. So for every 1 HClO4 that dissociates, I get 1 hydrogen and 1 ClO4 minus. So there we can see what the concentration of H is. So pH equals negative log of H plus, which in our case is negative negative log of 0.040 because it's equal. 1.40. All right. So that's how that works, quite easily. Strong acids, it's easy to calculate because it 100% ionizes. Strong bases, as seen on table 4.2 of the previous page, the most common soluble strong bases are ionic hydroxides of the alkaline metals and of the alkaline earth metals. So group 1 and 2 metals combine with hydroxides. These compounds, just like the acids, the strong acids, dissociate completely. Thus the solution label is 0.30 molar sodium hydroxide, contains 0.3 molar sodium ions and 0.3 molar of hydroxides. There is no NaOH left undissociated. So look at two examples here. We'll look at one involving 1:1 and another one involving a non-1:1 ratio. So sodium hydroxide, we can see here sodium hydroxide breaks down or dissociates into sodium ions and hydroxide ions. And it's 1:1, right? Because sodium is Na+, hydroxide is OH-. So if I know the concentration of sodium hydroxide that I'm working with, it is equivalent to sodium and hydroxide. So over here, now I want to find out the pH, right? Now there's a couple of different ways we can look at this. We could take a look at that formula sheet that we had the other day and kind of see what pathway we could take. So if we take a look at this schematic from the other day, so here's what we have. We have the hydroxide ion concentration, right? So if we want to figure out pH, there's two pathways we can go. We can use the ion product equation and then figure out the pH, or we could figure out the pOH first and then use this relationship to figure out the pH. But this one I think we'll go this way. So we'll use the ion product and then the pH. And then part B, we'll maybe go the opposite way just to show that it works. So over here we have OH. So the next thing to do is to figure out what H plus would be by using this relationship. So hydrogen ions multiplied by hydroxide ions give us 1.0 times 10 to the minus 14. So we have H plus multiplied by that, divide by 0.028, divide by 0.028. And what we get here is 3.57 times 10 to the minus 13 molar. So that's what the hydrogen ion concentration is. So once we know hydrogen ion concentration, we take the negative log of that to get pH. So pH is equal to the negative log of the hydrogen ion concentration. So we're going to put that in. It's a negative log of 3.57 times 10 to the minus 13, 12.45. Let's see, I'll round that up to 2 sigs. So we can see that is a pH of 12. And it's above 7, so yeah, that indicates a base, doesn't it? Anything above 7 is basic, anything below 7 is acidic. Let's look at the next one here. Calcium hydroxide. Now notice this is going to be a little bit different. Calcium hydroxide dissociates down, assuming it's a strong base, into calcium ions and hydroxide ions. But notice, hydroxides are -1, calciums are 2 positives. So for every 1 calcium hydroxide that dissociates, I get 1 calcium and 2 hydroxides. So if I know the concentration of the original calcium hydroxide, and knowing that it's a strong base, which I will tell you, 1 breaks down to give 1 and 2. So 0.0011 breaks down to give 0.0011. And 1 makes 2, 0.0011 makes 0.0022. So you can see how the ratio, we have to take that into consideration when doing that. Now for this one, I need to find pH again, right? So I have hydroxide. To figure out pH, let's go this route this time. Let's figure out the pOH first, And then knowing that it must add up to be 14 with the pH, I can get that. So POH is equal to the negative log of the hydroxide ion concentration. So POH equals negative log of 0.0022. That gives us 2.66. So that's POH. And knowing what POH is, then use this relationship here to easily figure out pH. This way, you may think this is kind of easier. Let's add an extra 0 there. So subtract 2.66, subtract 2.66, pH equals 11.34, and I'll round it up to 2 sigs again, so 11. All right, so there you have it. Strong acids, strong bases, completely ionized, and then we can figure out either the H plus concentration or OH, and then look at it. Most frequently we're being asked what the pH is, so we can use the right schematic off this formula sheet and go where we need to go using the right relationship. All right, you should be able to do the assignment now. See you again.